Hello, chemistry students. Let's try a Charles Law problem now. A 2-liter bottle filled with air is held at constant atmospheric pressure. If it is initially at room temperature 20 degrees Celsius, what volume will the gas take up if the bottle is put in a freezer at 0 degrees Celsius? So again, kind of like our Boyle's Law problem, how can we tell we have a Charles Law problem if the problem doesn't say which gas law to use? Again, first hint, look for what's being held constant. Constant atmospheric pressure. So Charles' law is the only one of our gas laws that involves constant pressure. Secondly, let's write down and label the information the problem gives us. A 2-liter bottle. All right, so I know liters is a volume. So volume 1, 2 liters. It's initially at room temperature. So we'll call that temperature 1, 20 degrees Celsius. What volume will the gas take up if the bottle is put in a freezer at 0 degrees Celsius? So we don't know volume 2. What volume will the gas take up if the bottle is put in a freezer at 0 degrees Celsius? So how can we tell we've got a Charles Law practice problem? Again, look at the information the problem gives us. We got volume, we got temperature. What does Charles' law say? At a constant pressure, volume and temperature are directly proportional. Our equation for Charles' law is going to look like this. Volume 1 over temperature 1 equals volume 2 over temperature 2. And volume and temperature are directly proportional. So let's use this to make a prediction. Directly proportional means if the temperature goes down, what should the volume do? Directly proportional? Volume should go down as well. So we're going to say prediction, volume will decrease. All right, we've got our data, we've got our equation. We're ready to start plugging in and crunching numbers, right? Almost. There's one more step we got to do first, and that is look at our temperatures. 20 degrees Celsius, 0 degrees Celsius. For Charles' law, we got to convert all of our temperatures to Kelvin. So if that's in Celsius, it's not too bad. All you do is just add 273. So the temperatures that we actually want to use for temperature 1, that's going to be 293 Kelvin. For temperature 2, 273 Kelvin. Now, let's plug our numbers in. Volume 1 is 2 liters over temperature 1, 293 Kelvin, equals volume 2, we don't know that, over temperature 2, 273 Kelvin. So to solve for volume 2, let's cross multiply. So our equation is going to end up looking like this. 2 times 273 equals 293 times volume 2. All right, calculator time. Left-hand side of our equation, 2 times 273, that's going to give me 546. Right-hand side of our equation, 293 times V2. To get V2 by itself, let's divide both sides by 293. So 546 divided by 293 gives me an answer of 1.86 for volume 2. Remember, guys, follow significant digits rules. We've got 3 significant digits in this, 3 significant digits in this. So let's round to 3 significant digits. Volume 2, 1.86. And then what's our unit going to be? Well, volume 1, a 2-liter bottle. So volume 2, that should be liters as well. So prediction, volume will decrease. Did our volume decrease? Yeah. Went from 2 liters to 1.86 liters. Again, imagine leaving like a football or a volleyball, something like that, outside on a really cold night. You're not changing the pressure, it's normal air pressure, but by decreasing the temperature, you're slowing those particles down. They're creating less pressure by colliding with the inside walls of the ball. So as temperature goes down, volume will go down. Hope this helps.